And today we're going to take a look into mesh density and accuracy versus speed. And in this webinar, we're going to go through mesh refinement, what it is, why we use it, when we use it. We're going to discuss high order elements, and then we're going to quantify the benefits of all of this by examining the analytical error. Mesh refinement, what is it? It's a simple process, an iterative process that we can use to analyze stress concentrations more effectively. And there's some benefits to our accuracy of answers, and there's also some drawbacks when it comes to computation time. So today we're going to look at a very simple example shown here. It's a plate with a hole in it. And now we're going to jump into Femap. So I have here a mid-surface of the solid that I just showed you, rectangular plate with our hole in it. And I want to show you one of the keys to mesh refining. So in Femap, there's a tool in the meshing toolbox here called geometry editing. And what we're going to do is we're going to add a washer to this hole, which will help us map the mesh around the hole so that we can get more accurate and better looking answers. So I'm going to use an offset distance of 0.2 because that's the mesh size that I want. I'm just going to click, and it's going to add our washer in there for us. So now I'm actually going to mesh this surface really quickly, a mapped mesh using a mesh size of 0.2, and our mesh property is going to be this plate property. And we'll just use the selector tool and grab all of our surfaces. And now we have a nice, beautiful mesh, and we are ready to run it. So I've already got the load in here, which is 1,000 pounds of tension, and we're just going to hit analyze. Should be done in a matter of seconds. Okay, so do take note of the time. It took about 0.4 seconds to run that, and if we go to our post-processing tab, actually activate our results. We'll go to post-processing. Using this result, we're going to look at the X normal stress. So if you take note of our coordinate system here, stress moving through the plate. We're going to turn that on. And this looks horrendous. So what we need to do is we need to update the material orientation for these elements. And we're going to put them in that X direction. And then we're going to transform into the material direction, update it. Okay. Turn off our geometry. And we'll take a look at our results vector. So what we can see is that we have indeed a stress concentration around this hole and a stress of about 1350 psi. And looking at it, we can see, if we zoom in, that there are high gradients across these single elements. And you can see how it goes from about the 900s range up to that 1400 or 1350 value across one element, which is a good indicator that we should probably refine our mesh and rerun it. So what we're going to do is in the mesh tab under editing, there's a command called element refine. And what Femap lets you do, one of the beauties of Femap, is that you can refine elements using a certain pattern. So what this will do is it'll split a quad element into 4 smaller quad elements, or you can do 9 elements, and it'll affect the elements on the outsides of it, adjusting so that your mesh flows cleanly. So we'll do this for all of these elements. Please select the elements. There you go. Okay. And that'll refine everything for us. Turn off that contour. And then we're just going to run it again. All right, fantastic. So again, taking note of the runtime. About 0.78 seconds, which is roughly twice as long as it took the previous one to run. Now, 0.3 seconds is a little unnoticeable, but we'll talk about later why this difference will compound when we get into more complex models. So we'll activate this guy, go into our post-processing tab, using the one we selected, same stress contour, or vector, we'll use the contour, and we'll look at it, and it shows us, okay, indeed a higher value. And if we zoom in, we can see the gradients a little bit less, but still kind of there. So this is the first step in the iterative process of mesh refinement, and you'll have to refine, rerun, until you converge on a value. But I've already done that to save us some time, and what we can see here is that with a very, very fine mesh size, we get a value of 2006. And so if we zoom in, just to show you what I'm talking about, we can see that there is a very, very small gradient running across each individual element, and that we've most likely captured our result. But instead of just taking our word for it, we're going to go back to the slides, and we're going to have a look at a graph. So what I've graphed here is the inverse of element size versus the peak stress that we saw around that stress concentration. And using simple stress concentration calculation, the theoretical max stress should be 2000 psi. And you can see that we basically converge on that value at a very small mesh size. I've also noted the percent error, which decreases as well from that 2000 value as we, decrease the mesh size. And what's also important to note is those degrees of freedom. We'll get to that in a little bit, but those are what's going to actually drive our computation time. Okay, so higher order elements. Higher order elements are, otherwise parabolic elements, are different than just a finer mesh. So instead of refining the mesh to have more elements, what we can do is we can add mid-side nodes to those elements to give us the same number of nodes, an increased number of degrees of freedom. But the benefit is that the assumed form of the solution becomes a second order shape function. I'm not going to get into all the details because I don't understand all of it myself, but using these two images here, hopefully I can show you kind of what I'm talking about. So on the left, we have linear elements, and all these corners are nodes. And in order to capture the behavior that was seen demonstrated, we need these 8 elements to kind of grab what's going on so that we can visualize it. However, using parabolic elements here on the right, we can eliminate a lot of the nodes a lot of the elements by just placing nodes on the mid sides and allowing it to use a second order shape function, assumed form of the solution, and we can turn 8 elements into 2 elements, and that helps us reduce our file sizes and our computation times. So to spare you the time that it would take to set up the parabolic elements and rerun everything, I've already gone ahead and done it, and now we're going to talk about the error that comes with all this. So I've got 2 lines here, one for the linear, one for the parabolic, and as you can see, we converge to just about the same value, that 2006 value. However, do take note that the parabolic elements start you off at a much closer answer, or a much closer value to the answer than the linear elements, and gets us there a little bit more quickly. So which one is better to use? Because see, we get the same answer, and I think the answer is both, to be honest. So now we're going to talk about split meshing. Split meshing is a technique that allows us to introduce 2 different mesh densities into a single part or model. And the benefit of that is that you get to keep the lower element count, the lower runtime of having coarse elements, but you get to introduce the accuracy that you need with fine elements around your concentration areas. So I've got two images down here just kind of showing you what split meshes can look like. And you can get into some complex stuff. The one on the left is transitioning between tetrahedral solids and hex solids, but that's a much different topic beyond the scope of what we're talking about today. So we're going to jump back into Femap, and I've already run our plate using the split mesh. So as you can see, I'm using, I think it's a 0.2 element size in the acreage and a 0.1 element size around the hole where the stress concentration is. And if we go back to the error slide, we can see that using just a 0.2 mesh size in the for the whole part, we get a value of about 1350 psi. And even though using parabolic elements, we only get about 1590. Whereas if we split the mesh densities and rerun it using this model, we can get about 1860. So we're already off on a better foot towards our converged answer than we were using, just the same element size across the whole thing. So going back to the slides, kind of an in conclusion slide. So the refining the mesh of your part will converge on a value which you can assume is the solution. And while this does increase your computation times, the goal is to get that increased accuracy. Now you noticed that, like I mentioned, the computation time increased just slightly using our model because it's very, very simple. But at the same time, when you move on to a large system model where you got a whole vehicle, a whole collection of parts, and small brackets or whatnot, you're gonna notice that those will increase exponentially, up to hours of runtime. So the benefits of split meshing really come into play there, where you can mesh smaller parts with more dense meshes, but at the same time you can keep your element count, node count, degree of freedom count kind of low. Also, the parabolic elements, you can use those to increase your accuracy. You can increase your confidence in your answer, but at the same time you get that increase in runtime. But it is to be noted that these can be situationally effective. So the real benefit to parabolic elements does come in when you have effects in between the nodes of the elements. Let me just show you guys real quick in this model. So we have our mesh here that's linear elements. You have nodes for each of the elements. Femap has another great tool where we can update these elements, and we can update their linear/parabolic order. This command will let us to change the order of the element. And we can grab all of our elements, hit OK. And since they're linear, it's defaulted us into the parabolic option. And we have this box checked that says add mid-side nodes. So the mid-side nodes are what allow us to gain the benefit of the shape functions that we mentioned earlier. And so we hit OK. And what you'll notice, I'll zoom in here for you guys to see, let it refresh. The elements now have these mid-side nodes. And so what we can learn from this, from using these frequently, is that when you have effects in between the two corner nodes of an element that need to be captured, that's when having those mid-side nodes really comes in to benefit, and where parabolic elements really kind of shine when it comes to increasing the accuracy of your results. So I did run a little bit quicker than I thought I was going to, but that's all I had for today, and I'm going to start taking questions now. So I believe it's in the questions tab of the GoToWebinar. You can type in your questions. And first question is from, I guess we won't read names. A mapped mesh versus a free mesh. So pulling up our model here, yeah, in the meshing toolbox under the mesh surface, there's two options: map mesh versus free mesh. So what the free mesh will do, and I can remesh here just to show you, is the free mesh. This is using the 0.2 elements. The free mesh will make whatever assumptions it wants to. So it's added in these two triangle elements, you can see. And tries are fine, but at the same time, using a mapped mesh will give us something that just looks a lot cleaner. And so Femap will give us more equal elements. It'll try and map to the geometry constraints that you've placed on the mesh, which in our case is that pad there's that washer that we put in there. Next question, I assume, is for this slide. Okay. What does DOF mean with respect to element meshing? So DOF, if you don't know, degrees of freedom. So the degrees of freedom when in finite element modeling are what actually are getting calculated, right? The translations and rotations of the nodes, which are the degrees of freedom, are what are actually getting calculated in the, if we go back here, we can see that in our results vector, that for each node, we're going to get translations, rotations, stress values, and the degrees of freedom are kind of what drive those calculations and what give us those answers. If that wasn't as comprehensive as you would like, we can get back to you on that. That one I'll have to get an email on you for. Here's a good one. How can you transition from linear elements to parabolic elements? So that's a little tricky because the idea of a parabolic element, as I mentioned, is that it assumes a form of a solution using a second order function, whereas the linear uses a first order function. So going in between those, it takes, just a different element type. So using this mesh size that I have here, we can, we'll just make these parabolic elements again. And so if I were to add another quad element onto the end of this, there would be a mid-side node on this element and not a mid-side node on the next element. So in order to transition between two different orders of mesh, let me see, over here my split mesh slide. This is kind of an example of that. So I've got tetrahedral elements in this model transitioning to hex elements, which is just 3D triangles to 3D rectangles. In order to do that, I've got pyramid elements in here. So these elements along here have a rectangular face that meets up with this rectangular face, but then has triangle faces to transition into the tetrahedrals. And in a plate mesh, it would be the same thing. You would have to put in, two different triangles, for instance. Actually, we'll do mesh copy node, copy this guy out this direction, and then we can make an element using, we'd have to use tri elements. To bring us down to a single node, and then we could do that here, add a triangle, and then we can transition into a different set of quads that doesn't have parabolic order. If you want more on that, I can get back to you in an email, but you'll have to retype a different question because if you want something further answered. Sorry, they're coming in, and I'm trying to read them as quickly as possible. again, a question, any reason why we can't just use parabolics where they're needed, i.e. near concentrations, while using linear elements everywhere else? Same thing to the same effect. That refined mesh that we had in the split mesh, you can add mid-side nodes into these and run them as parabolic elements, but you'd have to do that transition using tries, and not everybody loves tries. So it's kind of how you would feel it, like what you want to do. Oh, geez. That's a long question. Oscar, I'll have to get back to you on that after I actually read it. Are there any drawbacks to having too fine of a mesh in relation to the accuracy of a solution? Not that I've seen in my personal experience. However, not to say it couldn't occur. My initial thoughts would be something along the lines of whatever order you're using of element. Yeah, I don't know. I'd have to get back to you that on an email. Yeah, sorry. I understand what DOF is, but I didn't understand the numbering of DOF presented. So this isn't the number of degrees of freedom per element in this slide. So this is total degrees of freedom in there. So each node in a plate mesh will have 6 degrees of freedom, 3 translations, 3 rotations. And what I'm showing here is the total number of degrees of freedom. So that's to kind of demonstrate how your degrees of freedom will exponentially increase as you lower your mesh size, because you get 6 at every node. When you quadruple your nodes, you times 24 your degrees of freedom, globally speaking. Following up on the transition from linear to parabolic, is there a way that Femap can do this automatically? Unfortunately, I'm not aware, because yeah, you saw me do that manually. It might be possible, but I don't believe that I'm aware of a way to do it. We can, when I say we, I mean I can take a look into that and check some of these mesh settings on the mesh surface. Maybe some of these other tabs will have it, but I can get back to you on that via email.